Good afternoon, everyone. Now I think we have a good number to start. So let's begin this session. So before starting, let me first introduce. On behalf of the India Cooling Coalition and Alliance for Energy Efficient Economy, myself, Dr. Brijesh Pandey, currently working as Principal Research Associate at AEEE, extend a warm welcome to the CoolTech Webinar Series. For those joining us for the first time, the India Cooling Coalition is a dynamic multi-stakeholder group comprising non-profits, academic institutions, research organizations, and industry associations dedicated to advancing sustainable cooling research and application. With 23 member organizations, ICC works to accelerate the implementation of India Cooling Action Plan while addressing developmental challenges aligned with the global commitments like Kigali Amendment, the Paris Agreement, and the Sustainable Development Goal. The CoolTech webinar series is a part of this mission, fostering knowledge sharing on technological advancement and innovations within the cooling industry. Today's sessions, titled Enhancing Thermal Comfort and Energy Efficiency with Passive Cooling Strategies, will explore how passive cooling techniques can be tailored to specific climatic condition of India, building design, and local resources to achieve energy efficient cooling. This session will feature insights and case studies from distinguished speakers highlighting the real-world effectiveness of these passive measures and techniques. Before starting the session, I would like to announce the housekeeping rule. So each speaker will have a 15 minutes to share their insights, and the webinar will conclude with a combined question answers. Participant can drop their questions in the chat or ask them during the Q&A session. So before setting the context for this webinar, let me first introduce our eminent speakers. So we have first speaker Ms. Saswati Chaitya, Director as Green Tech Knowledge Solution Private Limited. Saswati is an architect and environmental planner with over 18 years of experience in energy efficient building design, embodied carbon studies, and building LCA. She led the Indo-Swiss Building Energy Efficiency Project during 2012 to 2020 and contributed to developing the Eco-Niva Samhita 2018 for the Bureau of Energy Efficiency. We have a second speaker, Mr. Monish. He is an architect and founder of Ant Studio and Coolant. Monish is a pioneer in nature-based energy-efficient cooling solutions. His work has received national and international recognition, including the National Energy Efficiency Innovation Award 2023, and he is also featured on Shark Tank India. As a TEDx speaker, he has presented his innovative ideas at forums such as the G20 Summit and the Science Museum London. We have a third speaker, Dr. Purva Keskar. She is an ESG strategist, architect, and director at VKE Environmental Solution. Dr. Keshkar specializes in environmental impact assessment, energy efficient buildings, and sustainable urban planning. She has been honored with awards like Green Champion Award 2019, Real Woman Award 2021, and contributes to national and local committees on sustainability and energy conservation. So before inviting our speaker, let me first set the context of this webinar. So we are aware that India faces a critical need to mainstream the passive building design as sustainable and cost-effective solution to achieve thermal comfort for all, especially given the country's high cooling demand and vulnerability to heat stress. With approximately 2200 cooling degree days annually and estimated 3 trillion person cooling degree days, the demand for affordable cooling solution is immense in India. I am also going to put some alarming statistics which further reinforce the urgency of this issue. So first is 11 out of the 15 warmest years in India have occurred since 2007, which highlights the intensifying impacts of the climate change. An study published in the Lancet estimates that significant number of deaths happen in India annually due to high temperatures. On 1st September 2023, India has an all-time peak power demand which reached to 240 gigawatt, driven by the cooling demand. 75% of Indian labor force work in the heat exposed sectors like agriculture, mining, construction, which makes thermal comfort essential for their productivity and well-being. Despite these challenges, we know that only 8 to 10% of Indian households have access to the air conditioning, emphasizing that the need for alternative cooling strategy is required. By focusing on passive building design, which leverages natural ventilation, shading, and thermal insulation, India can address these challenges in a sustainable and economically viable manner, while reducing dependency on energy-intensive cooling systems. This approach is critical to ensuring thermal comfort and enhancing resiliency to rising temperatures. In today's session as well, we will hear from our experts regarding how to address some of the status challenges and how they see passive measures to achieve thermal comfort India can be mainstream. So with this, before doing any further delay, I would like to invite Ms. Saswati Shettia to share her invites.
Thank you. I'll just try and share my screen. Just one moment. Can you share my screen? Can you see my screen?
Yes.
Okay, great. Good afternoon, everyone. My name is Sashwati and I'm director at Green Tech Knowledge Solutions Private Limited. Green Tech Knowledge Solutions Private Limited, we are a consultancy, research-based consultancy based in New Delhi, and these are all the things that we do. We have consultancies for sustainable building design, performance monitoring. We conduct LCA for buildings and for materials, capacity building. We have done policy advisory, and we have done large programs facilitating transition, the Indo-Swiss Building Energy Efficiency Program being one of them. So, since this entire session is about thermal comfort and passive cooling, and since this entire platform is about the cooling, the cooling actions in India, so I'll focus on energy efficiency in buildings, but looking at the thermal comfort aspect of it, and not we will not be looking at daylighting or any of the other things. So now when we talk about designing an energy efficient building, if say for example, there is X amount of energy that a business as usual building would consume, then in designing in order to make it energy efficient, there are three major steps that are involved. The first step is always to minimize energy requirements, which is done through passive measures. So you design the building envelope, the fabric in a way in which you won't require as much cooling. Now, since we're talking about the context is India, so we are talking about cooling, but anywhere in the world, through passive measures, wherever if it is a cold place, you would, minimize the heating requirement and all of that. So in India, we are talking about building design, passive building design, through which you would minimize your cooling energy requirement. And then, of course, there are times, and depending upon the location that the building is in, you may not be able to, provide comfort throughout the year in all seasons. There will still be some time, even with very good passive measures, you might still require some amount of cooling. In that case, you would use efficient cooling systems. And then the last bit is, of course, to use renewable energy for your whatever energy requirements that you finally have. So these are the three steps that we say in terms of designing an energy efficient building or even a net zero energy building. And the first and the most important step is always the first one, where we are talking about minimizing the energy requirement through passive measures. Now, buildings and specifically homes, and because Green Tech has worked a lot on residential buildings, had to be climate responsive or had to make use of passive design strategies till the time we invented technologies for cooling and heating and cheap artificial lighting. Before that, there was nothing that we could do. And so we had to build it in a way in which, it was more climate responsive and, do with passive measures itself. Now, just quickly for everybody, I mean, what are passive strategies? The passive strategies are methods of designing the building fabric that deploy principles of building physics to maximize the duration of comfort and minimize the duration of discomfort. And when we do that, when we maximize the duration of comfort hence minimizing the duration of discomfort, we eliminate the need to cool using fossil fuel based energy. So that is what we mean when we say passive measures. Now, passive cooling strategies, if I have to see what do these passive cooling strategies need to do in terms of principle, they need to do three things only. One, reduce solar radiation falling on the building envelope. Okay, so because the heat source that is coming into the major heat source that is uh, you know um, uh, uh, contributing to our discomfort is the heat coming from the sun. So the first step is reducing solar radiation falling on the building envelope itself. Then the second thing that a passive cooling strategy has to do is reduce external heat gains through the building envelope. So whatever solar radiation that has fallen on the building envelope, plus you do have temperature differences, the outside will be higher temperature than the insides, then in that case you also have to reduce the external heat gains through the building envelope, through the building fabric itself. And the third thing that needs to be done is that any heat that has come inside, any excess heat that has been generated inside the building, also through the use of various equipment, through the occupants themselves, that needs to be removed from the inside so that the occupants could be more comfortable. Now, how do we do these three things with the building envelope? So for reducing solar radiation falling on the building envelope, we have to avoid the radiation. That means also orient the building in a way, shade and reflect. For the second principle, which is to reduce external heat gains to the building envelope, we insulate and we also store and delay, meaning the thermal lag principle, thermal mass, use of thermal mass. And the third one is removing excess heat that has built up inside. So we open and ventilate. And what are the various building elements or features that we use in order to do all of these? It's all these things, these things that you see on your screen now. We make use of building and window orientation, building zoning, internal layouts, the materials of the wall, roof, windows, then window shading, sizing of windows, how much do we want our windows to open, and also we sometimes also make use of low energy ventilation design. So in the next few slides, what I'm going to do is that I'll take you through a few buildings examples of where passive strategies have been used, and also show you the impact of those passive strategies through monitored results. Okay, not just through simulation. We also did simulations for these projects while they were in the design phase, but we will also I'll be concentrating on the monitored results here. So the first building that I'll talk about is Madgar 3, Rajkot, which is an affordable housing project under the Pradhan Mantri Awas Yojana. Here, so there were 11 blocks, all about 7 stories tall. And the first thing which was already done before we came, Green Tech through the Indo-Swiss BEEP project came into the picture, was that the building blocks were already facing the north and south in terms of their longer faces. So that was already a check mark in terms of how in terms of proper orientation, especially given the climate of Rajkot, which falls in the composite climate. What else was used? Walls made of AAC blocks. So AAC blocks has a lower U value than, say, the conventional brick walls, and definitely much lower than, say, a monolithic concrete wall. So walls here. Second, taller partially glazed and casement windows instead of fully glazed sliding windows. With the proper orientation and the amount of solar radiation that was available outside, even that 1/3 of the glass was good for daylighting considerations. And since the climate of Rajkot also had very good wind regime, so more openable windows were suggested so that it could take full advantage of the natural ventilation potential in the cooler evenings. Then the third one, of course, is China mosaic finish on the roof to reflect the solar radiation falling on it. And what was the impact of these strategies? You will see that this is during the month of May in 2019. The red line, the red line shows the outside ambient temperature. The green one shows the temperatures measured inside one of the bedrooms. And this was a bedroom that was facing north. And you would also see that the lines, the blue, dark blue, and the light blue line shows the limits of the comfort band in this climate. So you will see that, except for a few hours, probably most of the hours during this period fell within the comfort band. In fact, a 90% comfort band for Rajkot. This was monitored, but when we also did predictive simulation, what we also said was that, okay, if the temperatures outside are, outside is 41 degrees Celsius, then with conventional building envelope, the inside temperatures would probably have been 38.3, around 38, 39 degrees Celsius. But with all these measures, it is actually 33 degrees Celsius peak summer temperature, which it's much more comfortable than the previous case. And, in many cases with a ceiling fan, you would still be able to, make do. And what it also does is that in the entire year, the number of comfortable hours increases dramatically with the use of these passive strategies. And this is for an affordable housing project where, most people would not be able to afford air conditioning. So this improved comfort really is of immense advantage to them. Also, another thing that we just tested out but did not implement on a large way is the fan assisted ventilation there for improved ventilation through the flats, even in the case of when there is not much wind outside. Then the second project I will be showing is Aranya Bhavan, Jaipur, which is the office building of the Rajasthan Forest Department in Jaipur. The monitored EPI is 43 kilowatt hour per meter square per year in 2015-16. For some comparison, the BEE 5-star rating for 5-star limit for buildings, for office buildings, is 90 kilowatt hour per meter square per year. The passive strategies used here were cavity walls with XPS insulation inside the cavity. We had an optimized load window to wall area ratio and double glazed windows. The roof was also insulated with puff insulation and had a light colored reflective roof finish. Now, one of the major impacts of the direct impacts of using all these passive strategies was actually there was a reduction in the chiller size, because this is a fully air conditioned building. But due to these passive strategies, there was a reduction of about 28% in the chiller size used in this building. So that is a direct impact of the passive strategies. The third one that I'm showing you is Ela Green School in Chennai. This is a private independent school, currently till class 8, and then sorry, there was some disturbance here, with plans to expand to class 12. Am I audible to everyone?
Yes, Saraswati, you are.
Okay, great. So here are the passive strategies that were used in this building. Super insulated, very very high performing envelope here with sandwich insulated sandwich walls, prefab sandwich walls actually used in this school. Insulated roof also, window glazing DGU in certain areas. Window to wall area ratio is 30%. It's not very low, but still okay, not too high. And our intervention, because this was already planned when Green Tech came into the picture, our intervention was to, make the windows much more openable, because this is Chennai, it is warm, humid area. So you would require much, better ventilation in this city. Apart from that, another thing that was done was, even this school, even though it had air conditioning, it was not like a fully air conditioned building. They were hoping to look at, using natural ventilation when applicable, or, hybrid cooling, that kind of thing. So here, what was done was, in each classroom, the shafts were proposed, which could be, used for an assisted natural ventilation mode also, where you would have these fans on the top of the shaft, which would induce, ventilation when the outside temperatures are okay, but the wind speed may not be high enough for wind driven ventilation just through the windows. So to assist in the natural ventilation, these shafts were proposed, and these shafts actually are used in this school for night ventilation. So when the students are not there, then during the night when the temperatures outside do go low, then this mode is used, so that when the students come in the next morning, the rooms are much cooler. These shafts can also be used to provide fresh air for during the time when this building would be air conditioned. So you could see in this picture that this is the shaft that we are talking about. Um, and the impact of better ventilation on this project was that the number of comfortable hours during the occupancy increased from 22% to 44%, and there was also 24% reduction in air conditioning load. Now, going forward, I would not look at particular buildings, but the monitored impact of certain strategies, certain passive strategies that we had tested out. So these are, external movable shading systems, right? So we say that, okay, shade your windows, and if, especially on the east and west side, where it is very difficult to shade the windows with only fixed systems, so it's easier to, it's better and more advantageous to have external movable shading systems. So we did, and just some examples of external movable shading system, including this from Rajkot, where you see that people have actually put in bed sheets and curtains outside their windows. We did test with external shading and with no external shading but internal curtains. What happens in that case? And this test was carried out in two flats, two exactly similar flats, one on top of the other, in rooms which were facing the same direction. So what is the impact of external movable shading system on internal operative temperatures? The room with NSYS was 3 degrees Celsius cooler on clear days. This was done for longer period. What the results that are shown on screen are for a week in June. The 3 degrees Celsius cooler on clear days. Impact on cooling. The room with the external movable shading system had 32% less cumulative cooling demand than the room with only internal curtains. Now, another passive strategy, the impact of which I'll show you through monitored results, is cool roof. This is, a test that we did in Andhra Pradesh over many affordable housing projects, small residential projects. And here you would see with and without cool roof, the overdeck, meaning the outside surface temperature of the roof, is 10 to 12 degrees Celsius cooler with the cool roof. And the underdeck temperature, meaning what the temperature of the inside surface of the roof, that is the one that is facing the room and which would actually have more impact on the comfort of the person sitting inside. The underdeck temperature of a cool roof was found to be 6 to 9 degrees Celsius cooler. Another example that I would show you is again from Rajkot, where we looked at two different housing projects, and you will see in the picture that the one here, the shorter one, is an apartment block made of monolithic concrete, and the one behind is a frame structure with AAC blocks as the walling material. And the results that we found here were this: that maximum indoor operative temperature, that is the peak temperature during a summer day, was 3 degrees Celsius lower in the AAC, in the flat with AAC, and the window to wall area ratio were more or less similar in both these apartments. One thing to keep note is that when we are talking about this kind of a thing, like the result that we are showing, we are also, it's not just because of the walling material, we are also making use of the natural ventilation potential. So yes, the windows are closed during the day when it is very hot, and in the evening the windows are opened. When this when we are also doing this, the operation of the windows are happening to take use of natural ventilation, then this is what happens. Your maximum indoor operative temperature is 3 degrees Celsius lower in the AAC flat, and the minimum temperature at night or early mornings is again 1.8 degrees Celsius lower in the flat with AAC walls. Impact on surface temperatures, and the reason why surface temperature is important is because we, the human skin, we have a lot of we transfer heat, we lose heat and gain heat a lot through radiative transfer. So the temperature of the surfaces all around us, the walls, the roof, and all of that, that holds great impact on our comfort within a space. So we also looked at the surface temperatures, and we saw that the maximum wall surface temperature was 4.5 degrees Celsius lower in the AAC flat, and the minimum wall surface temperature is 1.2 degrees Celsius lower in the AAC flat. So there are a lot of impacts, like very directly seen impacts on thermal comfort due to these passive strategies. And of course, the benefits extend to the cooling energy and the cooling demand that will be required with and without the passive strategies. I think I will end here. This was the last slide. Thank you.
Yeah, thank you, Saraswati, for presenting the wonderful slides and the number and figures that you have quoted in your slide. And we can get the sense that the passive strategies have the potential to reduce the active cooling system load. So with this, now I'm going to move towards our second speaker, Mr. Monish. And I would request my colleague to share his slides so that he can start his presentation.
Hi,
Yes, Monish.
a very good afternoon to everyone. Is my voice audible?
Yes, Monish.
Yeah. So, am I sharing the slides, or someone else is moving the slides? Can I try sharing my screen, or someone else is going to run them?
Yeah, please try moving your slide now.
Okay, we will just check this. If it doesn't work, then we can. Yeah. Is my slideshow visible?
Yes.
Okay. Great. So yeah, so this is Monish. I'm from Ant Studio. So today I'll be talking about thermal comfort and energy efficiency with passive cooling strategies, using specifically one project as a case study to talk about how we are implementing this. But before I go and talk about the project, something that we as a studio have been working on and researching is, while I think holistically we look at the entire building from on multiple aspects, but with a little bit more emphasis on building envelopes and how we can optimize the building envelopes to extract maximum efficiency out of it, is something that we try and do within the studio, and to see how we can pick up some of the traditional systems, especially jalis, and how we are integrating evaporative cooling with jalis, traditional jalis, and see how it can help in cutting the heat radiation into the building. So these are some of the works that how we have been using different kind of forms in the projects that we're doing right now at the envelope level. When I say at the envelope, where it involves shading, ventilation, evaporative cooling within the shading devices, and also to a certain extent roofs, how we can have control on that. So, but today I'll be talking about one specific product that we're implementing in a project called AeroLeaf, where these AeroLeafs are typically like louvers, but then they have this evaporative cooling happening from the surface of this. So wherein we are storing water, and so that the surface temperature of the building reduces, and it also helps in creating cooling effect as the air passes through this and comes inside. So this in one of the projects. So, and the whole idea has been that an average temperature at the building, like how we can reduce the radiation to see if in peak summers, about 6 to 8 degrees is what we have seen in temperature drop, in the difference between external temperature and after the envelope, how that is, we have checked it. And overall, the target has been, it varies from climate to climate and project to project, but then with the help of collective strategies, not one particular building envelope, and how we can try to reduce between 30 to 70% reduction in energy operations, this one in the building. So these are three verticals where we are focusing on building envelope cooling. And also recently we have started working on biophilic cooling towers and how we can take this into cool larger spaces, which I'm not going to be talking about today. And but public cooling art installations that can create a cooling effect. And these are the three things as a studio we're working on. Now moving to the envelopes. So these are four different strategies that we have been implementing. One is the system called as binary, where these are series of tiles, a lattice of the brick tiles, where we are dripping water on top of that, and as the air pressures and comes inside, it becomes cooler. And the first two techniques are pretty much similar, but with the variation in the geometry. And the other one we call as the beehive. These are a set of cones where again we are creating this evaporative cooling on the surface by dripping water on the through the cones. And whereas third, which I spoke about, is the aeroleaf, where it acts as a shading and lowers. But in this, the difference between this and the first two uh, products or the approaches is that in this case the water is contained within, so the direct evaporative losses are lesser, and also but at the same time there is much more control in terms of how we can orient the building, adjust the shading, how we can adjust the spacing between this vertical, so that we have also control on the amount of daylighting that we are letting inside the building. And as an architecture feature, it also has this control in terms of privacy and other stuff. So it has, but what we have noticed is that between the first two cases and this, the efficiency of evaporative cooling potential in the third case is relatively lesser as compared to the first two cases. In the first two cases, there is more water, more evaporative cooling, but in the third case, we have noticed that there is a substantial difference in terms of how much cooling effect that we can create through cooling evaporation. And the fourth case that we've also been recently exploring quite a bit is having these walls made of construction debris and recycled terracotta, making these walls made of this. And again, this is something very similar to gabion walls, but the only difference in this particular case is that we're using water to wet this debris that we are collecting, and also create these wet panels with the help of this that can help in making the envelopes porous and breathable and reduce the temperatures. So these are four different approaches in envelope cooling that we are trying. And now I'll be talking everything I spoke so far in one particular project that we are trying to do as a case study in Noida. The project is in Noida, and this we have done, and currently it is going to hit the ground soon, but in collaboration with our consultants, co-lead, who have been working on this project to analyze and optimize the building performance in this particular case. So this is the plan, and wherein the orientation is such that towards the left, sorry, the north, I think, is not marked in this. So the north is facing on towards the right, and then the south is the towards the left. So what the first very important strategy in this is, apart from cooling, we also wanted to cut down the embodied carbon inside the building quite drastically, reduce the amount of concrete that we are using. And strategically, in terms of design, how we can do it was the main core ideas that we have taken. So the objective has been to optimize both embodied carbon and also operational carbon. So as you can see, the ground floor plan, typically this is in a plot like this, wherein you have the built mass. These are the bylaws, how it allows. So you have covered area on the back, and then we have to leave a setback of 3 meters on the side for the driveway, and 4.5 meters in the front also for the driveway. But most of the cases, what happens is that this becomes covered with concrete, and there is not much space for landscaping. And like I said, I mean, there's a lot of concrete that comes in these areas. In this, strategically, we wanted to avoid making this plinth and reduce the amount of concrete in the whole building and also the basement that is there. So what we propose to the client is to leave this greenery without touching it with any kind of take the driveway on the right hand side into the stilt only in these two areas, and cover the rest of this area to be fully green, untouched. And also the building is designed in a manner that you can see that these three, if you can see my mouse, so we have removed this block like an island, what you see in the middle, to be segregated from the core and this building, so that there is cross ventilation and the potent lighting coming from all the sides. So in a plot like this, typically where you have ventilation happening from two sides, we wanted to achieve the cross ventilation and the lighting in most part of every single room in the building. So by detaching this block, we were able to create that cross ventilation in the draft and also bring to an extent daylighting throughout the day into most parts of the rooms, and every room in this building actually get access to natural light and ventilation. So this is the ground floor. What you see on the right is the first floor plan, wherein you can see that as you climb up to the core, there is a courtyard in the middle, and this block is segregated so that we have these again all the rooms and actually have a potential for ventilation, and also they face the courtyard in the center, and uh, and each and every bedroom, like I said, we managed to get ventilation and cross ventilation inside when it is desired. One very interesting aspect of this project, apart from trying to optimize the embodied carbon and operation carbon, is also that the nickname for this project, as we call it, is AQI project. And the reason for that being, when the client, most of us, I think, who live in Delhi and NCR, they know about the pollution crisis that we face, especially in this part of the year when in winters, and it becomes very unbearable. So the client wanted to have, while I think he's absolutely thrilled about this idea of a completely sustainable house, but he wanted to be the ventilation strategies and the cooling has to be completely controlled and not to depend on uh, natural ventilation throughout the year, because it is not possible. The air quality is not great. So to have this controlled, regulated airflow in the building and only to make it open when it is desired, and this is a practical constraint, and I think which most of us face these days. While I think most of us, when we talk about natural ventilation and passive, but the air quality doesn't let us open the building the way we wanted to, especially because of the kind of air that we breathe. So in this case, that also adds another layer of complexity to the brief, wherein we wanted to control the air and all that. So, and that is also become part of the brief. So as you can see in the when we are working on the form and optimizing it, we tested it for different areas, like different configurations to get maximum out of it. And finally, we decided to cut this block out and then create these spaces which are connected to this block, which can help us and have this. These are two other cases that we tried with different kind of courtyards and stuff, but we are not getting the kind of efficiency that we wanted in these two cases, where this becomes like a typical courtyard or a Z kind of a block. But this doesn't leave the same kind of quality of spaces that we are getting in the other case. And you can also see that we have checked it for different like the radiation into the building, and to see what is the best that we can actually get out in terms of trying to test it for different forms and how much radiation is hitting the building. There is also levels, I think, when I get into the 3D of the building, you'll get understand more from the perspective of how the shading is happening, the way the massing is done, so that the south and the southwest covers the rest of the blocks here. As you can see in the bottom case, the south and the southwest is taller, and it creates a shade on toward the eastern side of the building, creating a visual shade on top. And I'll skip through this and in terms of the heat gain of the courtyard and all. But so overall, in terms of the strategies, I think this is really important. What we tried doing is that while we having the courtyard and stuff, because of this having controlled environment into the whole space, we provided so that in the middle, while we're getting this, we created this courtyard and had this. Initially, we wanted this idea of a high-performing glass, but later we converted this into which I'm going to show you that as well, a passive downdraft cooling system on the top in the same space as a courtyard, so that we are using this courtyard also for like a wind catcher, so where we can actually catch the wind into it and supply to the rest of the areas. That way, we're able to get controlled environment into the space while this is the courtyard, but then the air that is there gets filtered with the help of that. I think the next slides talk more about it. And in terms of the overall thing, like I said, this courtyard was a very essential in terms of planning and the design, because we wanted to do that. But leaving it open like this also can compromise the air quality. So while we wanted to get the best of the efficiency from the lighting perspective and the daylighting, so we elevated this so there is the daylighting we're able to get, but the side walls have been created in such a manner so that we can get regulated airflow into the space with controlled passive downdraft, and that added a lot of character, I think, to the spaces. And at the bottom also, like we created this kind of passive this cooling system where we can have this what do you say, the cooling and controlled environment into the space. And Yeah, I think the site being in Noida, it is, I mean, we get all the seasons and it's predominantly hot and dry, but followed by, since, I mean, we have extreme climates all throughout the years, monsoons and also winters, and we are designing the building for all the areas. And so what we have done to cater to this is that seasonally we have provided solutions to the client, wherein for different parts of the year, there is evaporative cooling and also to an extent certain spaces of air conditioning to for hot and dry. And where with the natural fans and ventilation and with very limited air conditioning and also this passive downdraft wind catcher that we have provided on the top during for the rest of the seasons. So we have optimized it, making sure that with different strategies we have integrated into the building so that altogether we are able to optimize the amount of the thermal comfort using different strategies for different seasons. And in this, we also have tested like what is the kind of efficiency that we get just with the envelope that we're talking about. There is a reduction of about 12% only with the envelope for evaporative cooling envelope. But with the hybrid use of other strategies collectively together, and also the other strategies like passive downdraft and also other combined, we were able to reduce the efficiency of the building. I mean, the energy consumption by up to 32% approximately with using a hybrid mode. So this is the system that I was talking about on the roof, wherein the courtyard with a kind of a glass on the top that lets the light in. But on the side, we have this cooling, which draws the air, cools it with this wet pads that we created, and which on all the sides, it becomes like a wind catcher. And it pulls the air and we are able to channelize this to different rooms from the top. Apart from this on the courtyard, we also have this on the southern face, louvers, which I was talking about earlier in the presentation area, where it can work on the southern side, both for privacy from the adjacent building and also creates the shading and ventilation and cooling on the main southern face, which is facing the driveway. As you can see the cross section, this is the strategy that we have followed in the courtyard with this system on the top, wherein this with the cooling and the downdraft, it also can enhance the air quality because it's a wet screen. And we have this VRF unit that for other seasons, which can I mean, for mostly for the bedrooms, we're able to do it. And what you see in the cross section here, this is the southern wall, where this is able to cut the heat and maximum radiation that is coming to do. Yeah, I can see a hands up. Am I running out of time? Yeah.
Yeah, you can proceed, Anish.
Okay. There's not much left, so I'll just very quickly run through the rest of the slides. So yeah, apart from this, like I said, while this ventilation and cooling strategies are extremely essential, we also have recommended mostly every material in the project. I'm not going to get into the detail of this, but we propose AAC blocks, but we have tested it for different configurations to see what is the best one we can get, both in terms of the cost optimization and also in terms of efficiency. And ultimately, we have decided to go for AAC blocks because it reduces the load on the structure, hence also reducing the amount of the concrete that we are using in the building. And like I said, we have also very strategically, not just from an analysis perspective, also reduce the amount of concrete we are using the whole project with also having this pillar slabs, and restricted the basement depth only to 2.5 to 3 feet by elevating the building in such a manner, giving more space to the ground floor, so that we are not digging deep and having too much concrete in the basement, and only the basement is given only for the rear part. Strategically, in this particular case, I can show you only in the back part of this, what you see, these 2 bedrooms, this is the only area where there is basement. So that way we try to cut down on the amount of concrete and the that is used in the building as well. And the slabs, like I said, we are using filler slabs to get the best efficiency in terms of to reduce the concrete that is used in that particular material. And but yeah, I don't think we have the time to get into all of these details, so I'll skip through this. And apart from this, other strategies like solar and also can help, like we have implemented to get the maximum out of the roof. Yeah, strategies like this too. I was talking about the slabs in the building, which can help in both the insulation from the roof level, but also at the same time cutting the material. Yeah, this is how the overall building looks. These are the final images. So you can see that in the middle, the courtyard, this becomes like a sculpture in the center for the entry. And on the southern side, we have this skin that is coming that acts like this is not actually the final render, sorry. Yeah, this looks like this. So the southern side of this, we are cutting the heat that is coming, and at the same time, it's creating the privacy and the shading. And this step courtyards are actually facing towards the, so the whole building faces east. In this case, I think that's about it. Thank you.
Yeah, thanks, Monish, for showing us evaporative cooling in a very nice way to use as a passive measure technique. With this, now I would like to invite Dr. Purva Keshkar to share her insights on passive measure techniques.
Yeah, can you give me the sharing rights, please?
Yeah, please try from your end.
Yeah, I'm trying, but it only says that only meeting organizers can share, and I'm not getting those rights. Earlier, I was getting when I tried.
Okay, allow us a minute.
Should I leave and join again?
No, 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 that is not required.
Okay.
Now, please try again.
Yeah, now I'm getting. Hope my screen is visible.
Yes, it is.
You're able to hear me well?
Yes.
Yeah. So thank you for giving me this opportunity to share the little work that I'm doing, rather my company is doing in terms of affecting the mass housing as well as the commercial spaces in Pune in my area. So my job is made a little simple because I had two speakers earlier who have been talking about these concepts, and I won't go much in detail, but we all know that extreme heat is going to be likely there across India. And it means that there is going to be a power demand surge, which is going to happen. And therefore, China and India is predicted that the demand for air conditioning is going to increase. And typically, you see that the energy consumption for space cooling is really going to considerably increase. At one end, we don't have the energy, and for maintaining the security of energy for our country as well as the health, address the health issues because of heat stress, we really need to look at not only giving thermal comfort to people but also giving it at lesser costs. And what has this to do with the projects today that we built? Of course, Shashwati has already talked about, what were our precedents, where earlier you found that all the buildings, all the houses that were built had already integrated climate responsiveness into their design. And here we found that the form that was generated, the architectural aesthetics that was generated was because of the climate function, availability of materials and culture. And we were, having this kind of an approach where technology was respecting nature. And suddenly we started depending on the technology, and we find that master architects also started celebrating architecture by way of technology, where you see the elevators, right at the place, right at the corner of the building, like celebrating the technology. You have Mies van der Rohe making full use of glass and allowing people to enjoy the forest and yet, live in a space with a lot of security, safety, and thermal comfort. Then you have the Pompidou Center, where again a different kind of architectural aesthetic emerged. And that is a time when, modern movement where technology was used to serve man, and there was a lot of urbanization where we saw that technology started controlling the nature. This is what has happened today. We really don't know where we belong to. We are starting to lose our identity. World has become hot, flat, and crowded. Generally, that is what we say. And till we have a kind of identity, we will not have a feeling of belongingness. And a feeling of belongingness would generally generate a feeling of responsibility towards the natural resources, which we don't have. And that is exactly what Garden, who was a thinker way back in 1972, thought of and through his essay expressed. So here the contemporary architecture that we see is because of the want and not the need, and because of the ultra urbanization, where we have found that technology has started exploiting nature. Now the changed outlook. My earlier speaker already has given a different view in terms of how architectural aesthetics could be developed, harnessing the technology at one end and also the climate responsive approach, which needs to marry together if we really want to give thermal comfort and have energy efficiency at low cost. So I feel architecture has the power to address the issues of designing climate responsive built environment that offers thermal comfort and can tackle the heat stress conditions that are predicted because of climate change. It could also have the power to reduce energy consumption and do this at minimal costs. So with that, I'm going to show you a few projects, and I'm going to move really fast because I have 3 caselets with me. And this is a commercial IT park in Pune, and it's a very conventional scenario that you as a sustainability consultant and not as an architect of the project get approached when the building is almost done. You get 3D views to look at, and actually then you are supposed to kind of tell them, what needs to be done. And typically, as you know, that the green building rating systems generally are driving the commercial market towards energy efficiency, towards climate responsiveness, and I really give that rather I appreciate the green building rating systems for that. But at times what happens is when projects come to us for any green building rating, this is the scenario that you have a building in front of you with a 3D view. This is how the elevation was looking, and the plot typically, when you start looking at the plot, I'm going to show you, but first we start looking at the climate and we realize that we need to look at Pune being a temperate climate. Actually, it is marked as a composite, or rather a warm humid climate in ECBC or National Building Codes. But when there was a research done by Shakti Foundation a few years back, it was realized that Pune is moving from warm humid to composite. And as we all know that it was supposed to be a temperate kind of a climate. So looking at this kind of scenario, we understand that there are a few months where the comfort is not going to be offered because of the climate. And these are the months that one needs to tackle. So if you see the plot, it is completely a long plot, which is generally having larger facades to its east and west, which is not the right thing to happen, because we all know that east and west are the worst conditions to tackle in terms of energy efficiency. And here the heat ingress was going to be more. You see the north, which is tilted towards the left. And therefore, this long elongated building was really a great problem in terms of tackling how do you really tackle the facades. So this is the southwest facade, which was a problem. And of course, the northwest facade, which is going to be a problem. So we started looking at the northwest facade, and that was the only way we could, integrate energy efficiency and thermal comfort in the design, because there was no way of changing the design and changing the way the orientation of that building, because we all know that orientation is the first step that you take if you want to induce thermal comfort in any building. So we started looking at whether some changes in the southwest facade would affect or reduce the energy consumption of that building. And such kind of angles were given to the facade, which I'm going to show in a 3D later. So such kind of thing was done, and we started analyzing it for the months which were going to be really critical. And we realized that by doing this, we could reduce the WWR of the proposed facade to 15%. And then, of course, the shading percent increased to 12.3%, while as the radiation reduction happened to be around 15%, which, already Shashwati has mentioned about, that the first thing that you do is start looking at the solar radiation that is falling on the surface and then try and reduce the solar radiation by way of design of facades. This was the northeast facade. And then again, we started looking at how we can optimize the northeast facade by not really reducing a lot of glass, but trying to look at changing the angles of the glass and probably giving vertical, fins, which could really affect the solar radiation that is falling on the on that facade. So we started doing basic analysis of radiation and shadow, where we realized that this is a bare facade and you have an average shading of just 1.5% and average monthly incident radiation of 2,150, which then, because of the changes that we suggested, we could get it down to around 1,885 watt-hour per square meter, while as the shadow analysis showed that the average shading increased to 12% from 1.5%. Similarly, when we start looking at the northeast facade, we find that again here the radiation has reduced, the shadow has increased to 25%. So the first step was maybe look at the orientation of the north facade and try and, probably make it to an angle so that direct solar radiation is not falling on that facade. The shading and the overhang here was suggested to be 600 mm, which is a general conventional overhang which any developer is ready to do. And there was a WWR of 72% here. Then we started looking at whether we can have a overhang of 800 mm, which was slightly more than acceptable level. But then here we could reduce maybe the radiation. Further, we started looking at whether adding a spandrel could help. And then this reduced the WWR to 58%. So here is a summary of what was done. First, you have a bare facade, then you kind of make it to an angle and try and add some vertical fins, and then probably add a spandrel. And that would really get down your exposure to heat to 58%. The window shading could be 30%, and the solar radiation reduction could be 23%. And while doing this simultaneously, you have to keep a watch over the daylight, because the moment you start adding shading devices, it could affect the daylight inside any space. So with that, we started looking at the National Building Code benchmark, which said that 300 to 500 lux would be enough in any commercial space for the activities that are to be conducted in the space. And we realized that we were able to keep it down lesser than 500 and more than around 250, which is a good kind of lux level considering the activities happening inside the space. So we started with this facade, and the terraces that the architect had created were going to act like breakout spaces for the occupants, because this was an IT building and people wanted to come out into the terrace and enjoy a little open air and then go back again. But the problem was that these terraces were also going to be used to put in the outdoor units of the air conditioning. Now the problem is, once the ODUs go there, what is the kind of temperature that is there in the terraces, because the ODUs are going to leave heat in the terraces and probably reduce the usage of the terraces, because if the temperature really goes very high, people are not going to come out and be comfortable. So we did a bit of CFD analysis, and we tried to figure out what would be the temperature of the, at the terrace level. And this was going up to around 30 degrees Celsius. The average velocity here was around 1 meters per second. And we found that the average temperature with the ODU giving heat reject was around 30.82 degrees. So with this, we realized that we need to have some changes done to the way the outdoor units are placed. And typically, we suggested some vertical arrangements for the outdoor units. We thought of increasing the distance between the outdoor units. We also said that smaller louver spacing would help, and the angle of the louver spacing was also suggested, because we didn't want the people to have the direct draft coming out of these ODUs. So something where we started like this ended up like this. So this was a facade that was finally, kind of finalized on, and we started here and we ended like this. So a lot of work had to be done with the architect, and I feel that if the architect is open to suggestions, there is a different architectural grammar which can be developed, which has already been demonstrated by my earlier speaker. This is a second case study where we started looking at a knowledge park Pune, and very small changes, because when we're working with the developers, it may not be possible to make drastic changes, but we have to demonstrate how much it is really going to affect. And finally, what is the cost efficiency of the measures that you are suggesting? So you started with the conceptual model, you started, looking at predicting what is the kind of solar incident radiation with a spandrel of 1 meters and a 350 mm fin. And the other case, option 3, was 600 mm fin. And you realize that on the south facade, you have a reduction in radiation because of the fins and the spandrel. On the west facade again, east facade. So you start doing it for all the facades, and then probably you start looking at the peak glazing consumption. So you realize that the peak glazing consumption is also decreasing. And here you have a percentage saving of around 33.6% over the option 1, which was just the bare facade. While as if you have a 600 mm fin with 1 meter spandrel, you have a percentage saving of around 36.4 over the peak glazing consumption. You start doing it for south facade, and typically you'll find for the east facade, you have a percentage saving of almost 41.4% by just introducing a 1 meter spandrel and 600 mm fin on the facade. On west, again, you could get it down to 36%. So total cooling consumption reduction, which is the first case with 300 mm fin, which is generally acceptable to the developers, would give you a saving of around 7.5% in the cooling consumption, while annual heat gain through the windows could be reduced by 32.4% by just introducing 350 mm fins and 1 meter spandrel. So the cost savings that we realized after doing the kind of simulations, there was a cost saving of around 18 lakhs with a spandrel of 1 meter and 350 mm fin, while a cost saving of 19 lakhs with 1 meter spandrel and 600 mm fin. Now the developer can choose, and I think finally it was chosen that we could go ahead with 350 mm fin because it was also affecting the overall consumption drastically compared to 600 mm fin. So the cost benefit analysis pointed that we should use 350 mm fins. Now this is effect of WWR and shading devices in residential towers. And this was a project which we got, which was already designed. And then we said that, okay, let us look at which is a critical tower. And we realized that the critical tower is Tower A, which is facing the east and longer sides facing the east and the west. So this is a Tower A. We started looking at, WWR, which is the as-is case, which is 41% of WWR with a window sill of 750 mm. And it had a 450 mm box shading already designed with a EcoSense enhanced spring plus a Sahi float glass and a wall U value of 3.77 watts per meter Kelvin and a roof U value of 1.2. So you see here that there are 3 sliding, doors to it, and the sizes are given. And we said that, okay, let us only reduce the sliding doors, which was also talked by Shashwati, in her presentation. And here you find that with the as-is case, the building EPI was 62.1 kilowatt hour per square meter, while as the cooling EPI was 53.68. So you find here that moreover, the maximum energy consumption is required for cooling the space. So we decided that let us reduce the WWR to 35%, not much. So 41 to 35. And what we did was simply reduce the sliding doors by adding again a spandrel down there, opaque, a kind of an area on the sliding doors. And you realize that by reducing the sliding door, glazing, we could have a 8% decrease in annual heat gain, 3% reduction in cooling EPI, and almost 13 to 18% reduction in discomfort hours. So we started looking at discomfort hours, and we are now proposing that the developer should start writing these things in their marketing brochure, because comfortable hours would give them a better kind of acceptance by the client. So here the design cooling load, which was, you see that you have a percentage saving of almost 4% and no additional cost. We are in fact reducing the glass, and which was resulting in a monthly cost saving of around rupees 150 in a 3 BHK and 100 rupees in 2 BHK. So here is a discomfort hour analysis where you find that the percentage reduction in discomfort hours over the design case was 9.28% and going up to almost 18% by reducing the sliding door sizes. So case A versus case B, finally, building EPI 62.1 to 61.3 and cooling EPI from 53.83 to 52.3. So these are small numbers, but we have to demonstrate to the developer so that people start talking about it and expressing it in their marketing brochures, so that the end user also understand what benefits he is getting if he's buying in such a kind of an residential unit. So we said, okay, now we'll tell you that you have already made a shading device. If we remove that, what is going to happen? So here we removed the shading devices and we reduced the window sill to 450 mm. which is done here, and you realize that by reducing the sill level to 450 and no shading, there was an annual heat gain by 21%, 4% increase in cooling EPI, and 60 to 80% increase in discomfort hours. So by merely putting those shading devices, box shading devices, it is affecting the thermal comfort of people. Here you find that 9% increase in cooling consumption and 11% increase in cooling design load, while as monthly cost increase would be rupees 510 for a 3 BHK and rupees 350 for a 2 BHK. Discomfort hour analysis shows that by reducing the size of the window sill to 450 and no shading would give you a increase of discomfort hours by 62 to 75%. So similarly, it was done for a different, orientation. The earlier you saw for east, and now this is for west. So if there were no boxes and the sill was reduced, your EPI would really increase by 4%, and you would have a increase in discomfort hours as well. This is the third quick case study that I'm going to show, which is again a commercial building, but this was a little better because it was not a core and shell building. It was the owner's building, which was going to be operated and maintained by the owner. So here you found that the plan is very simple. There is a central atrium, and the beauty of this plan that because of this simplicity, we could integrate a lot of innovative air conditioned low energy cooling systems here. So in a simple square form, you start putting in the service areas as buffer zones on the west. So by doing simple box energy simulations, we realized that the cooling capacity could be reduced to almost 10.26% by way of improved glazing as well as roof insulation. We could achieve this. Now in Pune, we have never really, I don't think there is any building which has gone in for insulation in the walls. Here we were trying to promote that, but unfortunately the owner didn't really see a lot of benefit in that because we are also working with low energy cooling systems. And at times we also were going to use certain areas natural ventilation whenever the climate permitted us to do so. So here we found that because of the shading devices, the impact of shading devices could reduce the annual energy consumption by 8.84% and the cooling capacity by 8.11%. Different types of 3Ds or rather the facade designs were looked at, and we started looking at obstructed views and increased cost, and finally came out with the third option, which was actually going to give them most of the objectives that they wanted to achieve in their own building. There was a jali which was thought of, and we started looking at the opening in the jalis and how this opening in the jalis is going to affect the daylight that is going to come inside the room. We also started looking at what is the ceiling, how is the color of the ceiling or the interior objects or furniture going to affect the daylight which is coming in. And we realized that if the ceiling was done well, it could add to a lot of daylight and diffuse daylight into the interiors. So similarly, when we were trying to work out with the solar roof, we realized that if a roof is put in on the top, what would be the daylight under that roof? And we started looking at whether we need to give a cutout and so on and so forth, which would affect the design finally. Glazing selection, of course, like I said, we started looking at DGU as well as a single glazed unit and DGU plus jali and single glazed unit and jali. So we finally realized that there is not much of a difference if you are using a jali. You could yet go in and use a single glazed unit here for certain surfaces. The HVAC design here, we have a mixed mode of HVAC system, low energy cooling systems. The ground floor was typically using a earth air tunnel. It was designed for reception, indoor badminton court and game zone. And the fan capacity was 7,500 CFM and fan power here was 0.5 watts per CFM. Then we also, for the open offices, we tried to use the evaporative cooling. And then for the cabins which had multiple, rather diversity in occupancy, we use the air-cooled VRF. So HVAC system, you see that direct evaporative cooling was used for 65% of the space. The VRF was used for 22% of the space, and the earth air tunnel was used to cool 12% of the space. And therefore, typically 1 TR would generally be used to cool 250 square feet, but here we saw that 1 TR was used to cool 625 square feet. So this was the way the pipes were laid in, and we had a lot of problems because there was a little water coming out from the ground, which then had to be really sealed. So the pipes had to be really done really well before commissioning the entire system. So what I'm trying to say is that it does not integrating solar passive measures necessarily does not mean that it's going to limit you to your aesthetics. This is the way the building looks. So BLDC ceiling fans were integrated with grid ceiling wherever you had the evaporative cooling. The actual energy consumption again was metered and monitored, and you realize that we could go to almost near net zero for this building. So this is a cascading analysis where we started with 175 kilowatt hour per year, and we could get it down to almost 44 kilowatt hour per year with an integration of renewable energy system, taking care of 82.85% of the entire load. We also did an occupant comfort survey, which is very important because people's perception is more important. And we realized that, people were happy not only with the thermal comfort, but they were happy with the lighting conditions, and they were happy with the air quality of the space. So this was how the entire office looked. So at VKE Environmental, we believe that small changes can create big impacts, driving meaningful transformations over time. And this is what we do. So we are not only into environmental design, but we also do environmental clearances. We look at, ESG. So we start from strategizing the entire, operations, and then trickle down to maybe environmental design in terms of projects as one of the projects which would lead you to your ESG goals. With that, thank you. Thanks a lot. Hello. Hope you are able to hear me. Not able to hear you.
I can hear you.
Am I audible now?
Yes.
Yeah. So thank you, ma'am, for your presentation. Now I'm going to start the question answer session, and we have received few questions in the Q&A tab, and I am going to read out one by one, and the respective authors to whom the questions has been directed, and I would like to request the respective speaker to answer those questions. So starting from Purva ma'am, so this is regarding which tool was used to add in the design of Earth air tunnel system. Ma'am, you are mute.
So we have not really used any tool for that. It was hand calculations. We worked with the HVAC designer, and we started working with our hand calculations for that. Can't hear you. I think you're on mute.
Yeah. So this is the second question, which is like a common question. So any of you can answer this. So the question is, as we know, construction sector is dominated by the unorganized construction of individual homes. How do we convince such client for passive design strategies as cost involved is less and acceptance of this is less? What are the low cost passive strategies for smaller houses? So Monish or Purva, any one of you can answer this.
I think it's having information like this and analysis really helps in convincing people. At first, people not really know how much impact that they can create with smaller interventions like this. So having uh, what do you say, technical packing and analysis can actually make a case to convince people to, shift towards low energy systems.
Okay. Purva ma'am, would you like to add
Can you
points
repeat
on
the
this?
question again? I would like to take it, but can you repeat the question?
Yeah, the question is, as we know, construction sector is dominated by the unorganized construction of individual homes. How do we convince such client for passive design strategies as cost involved is less and acceptance of this is less? What are the low cost passive strategies for small houses?
Okay, so when we start thinking about small houses, we have to understand that already Shashwati and me, both of us have demonstrated that we need not really add to the cost for achieving thermal comfort, where we actually said that we should reduce the glazing, which is going to affect the cost because the cost of glazing is more than the wall at all points of time. So that's the first thing that we have to do. Secondly, I've also demonstrated that simply a reduction in your electricity bills by say maybe 150 rupees per month or 300 rupees per month is going to matter to small houses or other people staying in small houses. And these kind of figures and quantitative analysis will help us to convince people who are living in small houses. So that's number one. Second is in terms of, I think I've already answered by saying that, cost is not the criteria. The design does not require any kind of additional cost. So alertness and using quantitative methods, evidence-based methods to kind of come out with a solution which will actually make sense in terms of cost benefit analysis.
Okay. So for the questions directed to Saraswati, so she has to leave for this meeting for other commitments. So she has asked me to share the email IDs and she will respond to those questions individually. Moving forward, the next question is for Purva ma'am. What are the main barriers to adopting passive cooling and how do we overcome them?
So barriers is basically people not being aware that such kind of design can give them benefits in the operational phase. So I feel the life cycle analysis, life cycle cost analysis is very important to convince anyone for that matter for implementing any solar passive measures. Now, as I've already demonstrated that in some cases where the plot size kind of helps you do a right kind of orientation, there is no extra cost, right, for changing the orientation. But wherever the plot or the size and the shape of the plot is not allowing you to have an ideal orientation, then you have to start working with the facade. And working with the facade doesn't mean increase in cost. Again, I'm repeating this again and again, but solar passive measures need no convincing for that matter nowadays. You have to kind of work with the architect, and the architect himself should be convinced that it's going to make a difference.
Yeah, we have a long list of questions. Yeah, next question is for Monish. So the question is, how can passive cooling techniques uh, be made scalable for urban settings in India?
See, we have been working on some of these solutions, especially from an envelope perspective as a product. And one very important thing that we are trying to solve is, or at least trying to solve, is that uh, when we talk about architecture and practice, we always focus on buildings that are already or new buildings, and especially only for those clientele that can afford an architect or a designer in the first place. For most of the buildings where they do not have the luxury of bringing in on board a designer or an architect, in those cases, something like products or product-based approach could also help in reaching out to those people where uh, they can directly access these information and all, even if they don't have technical information throughout. So maybe by breaking down the consultancy and whatever practice, that the approach that we typically have, these otherwise the traditional practices, maybe innovative ways in which, like, if we can start looking at uh, coming up with solution strategies where we can actually address masses but not this one-on-one approach, could be a way forward. More product-based approach.
Can I add here?
Sure, ma'am.
I feel that wherever the owners cannot take architects on board, I think they need financial support, and this financial support comes from banks. So the banks should come out with schemes where probably they can give you guidelines, or this is a way you build if we were to give you the finance at some lower interest rates. And I think a few banks are already doing that, but such kind of schemes should actually reach the building owners, or the ones who are building on their own.
Yeah. Next question is again for Monish. So question is, for the evaporative cooling based envelope in general, what kind of challenges do you face with water supply and water use efficiency of the envelopes, and how do you manage them?
So definitely wherever there is water, it is difficult from a services perspective. One has to be very careful with um, like I mean, there are two things that we typically look at. One is the input of water and how do we take it out from the system and then recirculate it. The challenge that we face is that for low-rise buildings, it is very easy to handle. So we don't have to worry about for that, especially for small-scale buildings. But when the buildings become larger in scale and height, then definitely one has to be like really be careful about how evaporative cooling can be integrated into buildings. So that's a challenge that we face, and we are trying to resolve it by innovating within the product. But for small scale, I think that currently the tallest that we are doing is about 30 feet is the maximum height at the moment that we're addressing with evaporative cooling. Uh, but anything beyond that, we haven't done with. Uh, but there will be challenges because there is water, and then you have to be careful about uh, what do you say, the waterproofing issues, or um, the maintenance and all of that. This.
Yeah, it seems that audience are more troubling, Monish. So another question is for you. How is humidity handled in beehive and aeroleaf? Another
This is
technique.
okay. This is uh, actually not very difficult to do. It is really interesting that we have now timers and sensors and clocks, which where we can regulate the amount of water to the precision of a seconds. So in fact, in most of the systems that we do right now, based on the height, we release the water for a few seconds. I'll give an example. For example, for a 15 feet wall, we release the water for 3 seconds, but that's the amount of time the water travels from the top to bottom. And we cut off for next the frequency based on the humidity and the season that is there. So if you want more humidity and if it is dry, then the frequency reduces so that you're releasing water quite regularly. But if it is like humid areas, then the season is like monsoons, then the frequency can even go up to minutes. So we release the water for 3 to 5 seconds, and then we stop the water for next 60 seconds. So that frequency can help in regulating the amount of water flow, controlling the amount of humidity they're releasing into the environment.
Now, I'm requesting other peoples who have a question in their mind, they can raise their hand, and we will allow a couple of one or two more questions, and then we will wrap it up. Yes, Ayush. Ayush, you can.
Yeah. Hi. So my question is for Saraswati ma'am. So my question is for her that.
Unfortunately, Ayush, unfortunately, Saraswati has left.
Okay.
So if you
Yeah.
have
Any
another
of
question,
even
or-
Purva ma'am and Monish sir can answer this. So
yeah,
my
sure.
question was regarding the difference in the simulations and the actual monitored observations for any kind of a project. So, like any case studies or any something study where you have observed that there is not a favorable thing happening, what was observed in the simulations, and it is not reflecting in the actual case.
Actually, already Shashwati has shown that she already did some predictive evidence-based, analysis, and then she has already put in some, monitored by way of actually going and placing sensors, and she has shown that it has worked, in a similar way. Now, where it changes is, when we are working with our predictive models, at times, the occupancy is a little different. This is what happened with us when we were working with Enpro building. First few 6 months, the occupancy of the building was less. And we couldn't really, understand whether what we had predicted was, similar to what was happening on ground. So there are many aspects at times where over the period of time, certain things changes. The maintenance of the, technologies are to be done frequently. And such things do affect you know, uh, the evidence-based results that we have even before. So the predictive evidence-based results that we have. But I feel that the trajectory or the logic with which things are changing in a predictive model is similar to what is happening on ground.
Yeah, thank you, ma'am. Sir, one question to you, Monish sir. As you mentioned that it is a bit tricky to use the water that has been used for the tiles that you propose, but are any case studies or on a larger scale picture where the treated wastewater has been used for this purpose? Because the quality of water also would have been mattered for such a product to be used.
We haven't used treated wastewater because for two reasons. One, it is really good for when you talk about, especially we also do some biophilic installations, and there in that case it's very nice because it helps in growth of like moss and cultivating plants and all of that. But it is not a very good solution for when you look at the air quality and guess what kind of uh, how it can impact. It'll become a very complex subject from a health perspective. So for that reason, we haven't actually not recommended or used treated wastewater for this purpose, because it can have, while cooling and is one aspect, but we did not want to get into the trouble of having any kind of pathogens that are released that can have impact on the breathing issues of people. So that is something. But talking about also the previous question on the predictive results, I can just say one thing, that earlier when we started our practice, there used to be a massive difference in the what we're doing the analysis and what we got in their site, because ultimately this predictive results is all proportional to the amount of clarity that you can bring into the software. If your assumptions and the numbers that you're feeding in is not actually as in-depth to the site conditions, the results that you get are also going to be inaccurate. And with over time, what we realized is with the more and more experience of dealing with things, you are starting to get more and more grip on trying to evaluate the built environment in a much more constructive manner. So, but in the earlier stages, what we realized is there used to be huge blunders even in the analysis that we have conducted, so that the approach was wrong. And with more and more data that you're feeding and more parameters that are there, you're able to starting to get much more better results that ways.
Yeah, so due to time constraint, now I would like to wrap up this session. And also, I am requesting Monish and Purva ma'am to uh, share very brief the key takeaway message for the participant, and then we will wrap this session.
So I can say that solar integration, solar passive, measures in any building is no rocket science. It's just simple kind of observations that you see, feel, and experience, and you integrate in your design. Second is it doesn't require any additional cost. And this is, I think, the most cost efficient way of integrating energy efficiency and thermal comfort into any building, not only looking at thermal comfort, but giving the feeling of experience by way of using these measures as an aesthetical grammar, using it to create some kind of aesthetics for your project is a opportunity that architects should look at. Thank you.
Thanks, ma'am. Monish?
Yeah, I would like to just say that I'm not an energy consultant, I'm an architect. And in the earlier stages of my practice, when we used to go to the clients with some of these strategies, there is always this question about convincing them, because ultimately you are suggesting things which are whimsical without any backing. And especially with having data and the method of convincing them with numbers makes it much more stronger convincing case to convince people, because then there is no if and but. When you're going with, then it's not no more a questionable strategy that you're applying to a project. So while it is absolutely very simple, most of the strategies that are there that are common sense, and in traditional knowledge we have access to many of these systems, but having data and data-driven approach to any kind of a problem can help make us a strong case to the clients and give a very convincing pitch.
Yeah, sure. So with this, thank you to all our speakers for their insightful presentation, and to the audience also for their active participation. The discussion today underscored the potential of passive cooling strategies to enhance thermal comfort while promoting energy efficiency in buildings. On behalf of ICC and AEEE, I extend my heartfelt thanks to everyone for making this webinar a successful event. We look forward to seeing you in our upcoming sessions. Thank you and have a great day ahead.
Thank you.
Thank you.